r and phi from 0 to 2 pi. But Txz is given by that. And just look at the integration with respect to phi, cosine of phi d phi, from 0 to 2 pi. 0. So that tells you it's 0. Now look at over Fy, over the plane of T dotted dA of y component, that's going to be from 0 to r, from 0 to 2 pi with the minus sign, and that should be Tyz r dr d phi. And that, if you look at Tyz, that's what you have. And again, first if you integrate with respect to phi, because of the sine phi term, that's also going to be 0. Right? So this is going to be 0. But for the z component, Fz, so that's going to be over the plane of T dotted dA over 0 to r, 0 to 2 pi of Ty Tzz, which has this component. So that's going to be 1 over 2 epsilon naught Qr over 4 pi r2 squared. So r dr d. The reason why I wrote this one is because this is a function of theta, but we are doing it on the plane, and on the plane we say theta is pi over 2. So when you say pi over 2 equals to 0, so this term will get to 0, so you will end up with that one. So when we substitute that in here with the minus sign, and the minus sign that comes from the area here, so this minus sign along with that minus sign, you get a positive integral. So what you would end up for the force is going to be Fz, F in general is going to be just Fz d hat. So you find 1 over 4 pi epsilon naught r2 squared over 16r squared r ln d hat. So now we did the integration over the entire surface. So the total force is going to be whatever we found here for the spherical surface plus on the plane surface, and that will give you this result. So this is the final result of the force. So of course, we obtain this result using just a simple application of Coulomb's law, but this is how we do it in terms of the Maxwell stress tensor. All right, so now one important conservation law, that's conservation of momentum. So, and we also see conservation of angular momentum. So from Newton's second law, how do we define force in terms of a mechanical change in momentum? All right? Conservation of linear momentum. This is linear momentum. So from classical mechanics, it tells you that all the forces acting on a given object, that must be equal to the change in the mechanical momentum. P mechanical with respect to time. Right? So that's just Newton's second law. But we just found out the force in electrodynamics is given by the stress tensor, and we know that T is equals to the integral of the Maxwell stress tensor dot dA and what? Minus 1 over the speed of light squared, and d with respect to time of the integral of the Poynting vector s d tau. All right. So if we equate this to the change in the change in mechanical momentum. Remember, this is just the mechanical momentum, and this one. So if I substitute this one here, I would have m e. When you say mechanical momentum, it refers to the momentum due to either some translational motion or some rotational motion. That's what when we talk about mechanical momentum. So the momentum due to as result of motion. So that momentum change with respect to time must be equal to the total force, which is related to the electric fields and also the Maxwell stress tensor. So that's going to be T dot dA minus 1 over c squared d by dt of s d tau. All right. So now, if I just looking at the dimension for this side, and also looking at that, if I rewrite this one, T dot dA minus d by dt of 1 over c squared, the integral s d tau. What can you say about this? Remember, we have here change in momentum with respect to time, mechanical momentum, and you should expect the same dimension in here, right? So you have this change with respect to time of some quantity in here. So what can you make a conclusion here for this one? Momentum of the electromagnetic fields. So you can define this as P of the electromagnetic fields as 1 over c squared times the integral of s d tau. And in terms of that, then I can write this as dPE, dPME with respect to time is equals to the integral of the Maxwell stress tensor dot dA and minus of dPEM by dt.